Okay, we've learned that Ohm's law, KVL, and KCL can be applied to the frequency domain. So let's work a few problems using mesh analysis and nodal analysis to show how to do phasor problems. So let's begin first with nodal analysis. So let's do a nodal problem, and let's make this one kind of straightforward to begin with. So I want to find the voltage V and currents I1, I2, and I3. Given that this current, IS, is equal to the following. IS is equal to 8 times cosine 200,000 T amps. So we're going to work this and get a time domain solution, but we're going to do it by going through frequency domain analysis. So talked before about how Steinmetz's brilliant idea was to add an imaginary source and then extract the real portion from the response, from the solution. So we're going to do that, but we're not going to go through all those little intermediate steps. As you're going to see, it's very straightforward how we do that. So in this case, we first take this circuit and we convert it to the frequency domain, which means that every element has to be switched over to its frequency domain equivalent. So in this case, let's do that. We're going to get IS, the voltage V, current I1, current I2, current I3. Now what's IS equal to? Well, in this case, we can look right up here and we can write the phasor for IS right out of this. So IS is going to be equal to 8 at a phase angle of 0 degrees amps. Phase angle is 0. And we note here that omega by inspection must be equal to 200 kiloradians per second. Okay, now 8 at a phase angle of 0. Let's convert that to rectangular form. That's going to be 8 cosine 0 degrees plus j times 8 sine 0 degrees. That's equal to 0. This is equal to 1, and therefore IS is just equal to 8 amps. And I want to emphasize that's not 8 amps DC. That's 8 amps as in the rectangular form of the phasor. The 10 ohm and the 6 ohm resistor are not going to change in the frequency domain. But the 40 microhenry inductor becomes an impedance of J8 ohms. And the capacitor becomes an impedance of minus J5 ohms. And of course, this is equal to J omega times L, and this is equal to minus J over omega C. So I'm just using the impedance formulas and plugging in the numbers. So now I have transformed this over to its frequency domain equivalents. And let me just go ahead and fill those in. Okay, so now we're completely in the frequency domain. I've just erased the time domain values on the schematic. And now let's go through and let's solve this. And in this case, I'm just going to use Nodal Analysis. I've got two essential nodes. I'll just pick the bottom one. According to my voltage definition, the top node is going to be equal to V. And what I'm going to have then is that 8 is equal to V over 10 plus V over 6 plus J8 plus V over minus J5. And now I solve this, put this into Mathematica, and what I'll get is that V is equal to 32 minus J 24 volts. Now, Mathematica works strictly in rectangular form. So equations will come out in rectangular format. If you want to convert them over to polar form, the easiest way to do that is to use a calculator. And if I do that, I shall get that this is equal to 40 at a phase angle of minus 36.87 degrees volts. I1 will be equal to V over 10, and that's going to be equal to 4 at a phase angle of minus 36.87 degrees amps. I2 will be equal to V over 6 plus J8, which will be equal to minus J4, which will be equal to 4 at a phase angle of minus 90 degrees amps. And finally, I3, which I'll put up here. I3 will be equal to V over minus J5, and that'll be equal to 4.8 plus J 6.4 amps, which will be equal to 8 at a phase angle of 53.13 degrees amps. So I have all my results in phasor form for all the voltages and currents. And now that I have these results, I can now get the time domain by simply taking the magnitude and the phase angle and then plugging them back into their time domain equivalents. And so what I will get is this. V is equal to 40 cosine $200,000 T minus 36.87 degrees volts. I1 is equal to 4 cosine 200,000 T minus 36.87 degrees amps. I2 is equal to 4 cosine 200,000 T minus 90 degrees amps. And I3 is equal to 8 times cosine 200,000 T plus 53.13 degrees amps. And there's my result. So here are my time domain solutions. Instead of writing several equations and trying to solve parallel equations using differential equations and trying to solve those simultaneously, instead it just becomes an algebra problem. I just go through, calculate these quantities, and then convert, taking the magnitude and the phase angle and plugging right back in. And notice the cosine 200,000 T, that amount carries forth in the response, which is what we would expect from a linear circuit. So here we see in a nutshell what we're going to be doing. The methodology is the same. All we're doing is we're working in using complex numbers, we're using complex algebra, and then we're solving and putting everything in phasor format to get it back to the time domain. All right. Let's work another problem. Let's do a mesh analysis problem. So let's do a mesh analysis problem. Once again, we're going to do a phasor response. And some problems you will start in the time domain and go to the frequency domain and come back. Other problems, you're just given the problem in phasor form to begin with. So in this case, let's do this particular problem. And for this one, we're going to have a dependent source. This will be 39 times Ix. And this is 1 ohm, J 2 ohms, 1 ohm, J 3 ohms. And this is 12 ohms, and this is minus J 16 ohms. So I want to find the following voltages. I want to find V1, which is the voltage across these two elements, V2, the voltage across these two elements, and V3, the voltage across these two elements. And I want to find V1, V2, and V3 using mesh analysis. So let's do that. In this case, I'll define two currents, two meshes. I'm going to call this one I1, call that one I2. So let's write our KVL equations. So for my I1, okay, I'm just for these elements that span these two meshes, since V2 is already defined, I'm just going with that definition as far as defining the polarity across those two elements when I go through and write the KVL. So this 150 at 0 degrees in rectangular form is just 150 volts. So in this case, 150 is a rise, and that's equal to 1 plus J2 times I1 plus 12 minus J16. And the way I'm defining the voltage polarity, it'll be I1 minus I2. Then for my I2, I will have, in this case, 12 minus J16 times I1 minus I2 is now a rise going around the I2, and that will be equal to 1 plus J3 times I2 plus 39 Ix. And now I need my dependent source variable equation, which says that Ix is equal to I1 minus I2. So this is nothing more than your conventional mesh analysis problem, just we're solving it with complex algebra. And if you solve this, what you'll get is that I1 is equal to minus 26 minus J 52 amps. I2 is equal to minus 24 minus J 58 amps. And Ix is equal to minus 2 plus J 6 amps. So those are my currents I get, my mesh currents plus my Ix current. And now I solve for V1, V2, and V3 just using Ohm's law. So V1 is equal to I1 times 1 plus J2 will be equal to 78 minus J 104 volts. V2 is equal to Ix times 12 minus J 16. That's equal to 72 plus J 104 volts. And V3 will be equal to I2 times 1 plus J3, which is equal to 150 minus J 130 volts. And there's our answer. And incidentally, we can always go through and check these kinds of answers by just making sure that KVL makes sense. So for example, we look at this. How do I know I got the correct answer? Well, does 150 equal to V1 plus V2? Okay. So, just do a check. Is 150 equal to V1 plus V2? So 78 plus 72, 150 minus J104 plus J104, they cancel? Yes. So the KVL for I1 mesh works. What about, does V2 equal to V3 plus 39 Ix? And you plug the numbers in, and what you'll find is, yes, that balances as well. So you can actually go through and add these numbers together and see, do they work? Just a simple way to check. Same thing with a nodal analysis problem. Actually, once you get the numerical values of the currents, find out, are you meeting KCl correctly at every node? Does it balance out? So it's always useful to do in these kinds of checks, just when you have enough time to make sure you didn't make a simple math error. And if it turns out that one of these KVL or KCl equations doesn't work out, then look at the equations for that particular mesh or that particular node. Okay? So, as we can see here, the methodology for nodal and mesh doesn't change at all. It's all just complex algebra. But let me do another problem just to kind of illustrate the kinds of neat little tricks you can do with frequency domain analysis. So, let's, for example, let's work this problem. What if we had a problem like this? Okay, so I've got 2 millihenry, 1 ohm, 2 times cosine 10 to the 4th t milliamps, 5 times cosine 10 to the 4th t volts for that source, 8 ohms, 5 ohms, 15 microfarads, 74 microfarads. And here's what I want to find out. We've got a 1 ohm resistor here. Let's find the power in that 1 ohm resistor at t equal 1 millisecond. Now, before you learned phasor analysis, this would be the kind of problem that you just could not really tackle, because you'd be solving multiple equations, multiple differential equations simultaneously in order to try to get some kind of result that you could solve this with. But in this case, we're going to use phasor analysis to make this easy for ourselves. So let's consider what we want to try to do here. I'm going to define a current I sub r and a voltage V sub r across that resistor. And we know that the power of that 1 ohm resistor at any time t will need to be equal to VR of t times IR of t, or IR squared t times 1 ohm, or VR squared t divided by 1 ohm. So we already have the formulas for how to calculate the power in the resistor. We're just going to calculate the time domain quantities. And really all I have to do is either find IR or VR and then just plug it into one of these formulas. How are we going to do that? We're going to find IR or VR as a time domain quantity through the use of phasors. So let's convert this over to the frequency domain so we can calculate one of these two quantities. So in this case, we note omega is equal to 10 to the 4th. Now notice in a phasor problem, if you have more than one source, they've all got to have the same value of omega in order to work the problem. So in this case, omega is equal to 10 to the 4th radians per second. All right, since we know that, I can now go and convert everything here into phasor format, frequency domain format. So in this case, this becomes 2, actually since it's milliamps, this becomes 0.002 amps. So it's 0.002 at a phase angle of 0, and we just write it as 0.002. This becomes 5 at a phase angle of 0 degrees is equal to 5 volts, just as, of course, this became 0.002 amps. So that phase angle of 0 degrees. The resistors don't change. This, of course, becomes VR phasor. This becomes IR phasor. The 2 millihenries becomes J 20 ohms when I put it into the J omega L equation. And this becomes minus J 6.667 ohms. And this becomes minus J 1.351 ohms. All right, so I've converted all my values over to phasor domain, over to the frequency domain. And now I can go through and solve this. And when you look at a problem like this, many people, their first impulse would be to put the ground on the bottom node. But really, a better node is this one. I'm going to ground this node, because that lets me define this top node. This now becomes minus 5 volts when we look at the polarity of that voltage source. And now I'm going to pick some current directions. And now I'm ready to write my nodal equations. I'm going to define this node voltage as V1. This node on the bottom I'll call V2, this entire bottom node. And this becomes V3 at that node. So I've basically put a little bit of effort into here. I've set everything up. I've taken everything and transferred it over to the frequency domain. Now I'm going to write my KCl equations. So in this case, what I'm going to get for my KCl is that at V1, for my V1 node, 0.002 going in must be equal to V1 over 8 plus V1 minus V2 over 1 plus J20. For the V2 node, I've got V3 minus V2 over minus J 1.351. Plus V1 minus V2 over 1 plus J20. Must be equal to the current going out, which is 0.002. All right. V3. For my V3 node, I have that V3 minus -5 divided by minus J 6.667 plus V3 over 5 plus V3 minus V2 over minus J 1.351 is equal to 0. So a little bit messy with the complex algebra, but these are just standard KCl equations. And now that I've got these, I can solve, and I get the following voltages. So if I solve, I get that V1 is equal to minus 1.168 plus J 0.008177 volts. V2 is equal to minus 1.336 minus J 2.951 volts. And V3 is equal to minus 1.335 minus J 2.754 volts. So I've calculated my voltages. IR can now easily be calculated given V1 and V2. And so what I have is that IR is equal to V1 minus V2 over 1 plus J20, which will be equal to 0.148 minus J 0.001022 amps, which in turn is equal to 0.148 at a phase angle of minus 0.395 degrees amps. And from here, I can write IR of T. IR of T can be directly written is equal to 0.148 times cosine 10 to the 4th T minus 0.395 degrees amps. So now I'm just going to calculate the value of that current at 1 millisecond. That's what we wanted to find. So IR at 0.0001 seconds will be equal to minus 124.24 milliamps. And therefore, the power in the resistor at 1 millisecond will just be equal to minus 124.24 milliamps squared times 1 ohm will be equal to 15.435 milliwatts. And there's our result. With a mathematical tool like Mathematica and writing the equations, doing this in the frequency domain makes this problem very straightforward to do, as opposed to having to do it the hard way with calculus. So here is really, kind of a really more complex problem that illustrates the real utility and the real power of this type of analysis. But again, nothing we're doing here is anything different than what you've done before. We're just now doing things in the frequency domain instead of the time domain, but the techniques are the same. Okay, so nodal analysis and mesh analysis work as we expect. And if we now look at more advanced circuit analysis techniques, we'll see that we can also apply them just as we did before. So we'll start looking at things like source transformation and Thevenin's theorem next time.